These notes are on properties of radicals. This is section 9.1, so this is the first section of the next chapter, which is all about, we've been working on graphing quadratics or parabolas, but now we're going to be solving quadratics. So before we get to solving, we do have to build kind of a background understanding on radicals. And we have done some stuff on radicals, right? We've done simplifying square roots. We've worked on rational exponents. So that's all in previous chapters. But what are the various properties that radicals have when you simplify them? Okay. So the first thing is what is a radical expression? A radical expression is an expression that contains a radical. An expression involving a radical with index n. I'm going to draw an example off to the left. Is in simplest form when these conditions are met. It has to have each one of these things. So number one, no radicand. Have perfect nth powers as factors other than 1. So let's talk about radicand. So when you have, I'm calling it a square root, but generally it's just called a radical. The radicand is the number that's on the inside, right? So we did that in a previous section before. And we mentioned index. The index is the number that is kind of outside of the radical. This is typically written as a rational exponent. This would be the denominator. But for a square root, it's a 2. For a cube root, it's a 3, and so on. So what it's saying is like nothing inside has a perfect nth factor. So, right, if we're talking about squares, right, so squares are, right, 1 squared is 1, 2 squared is 4, 3 squared is 9. Those are not inside because we can simplify that further. All right, we don't need that for now. Number 2, no radicands contain fractions. There is a way you can simplify fractions that are in a square root or some other type of root. And there is a proper way of writing it in simplest form. We'll talk about that at the end of the notes. And then number 3, no radicals appear in the denominator of a fraction. Right? So no radical can be in the bottom of a fraction. So if I draw a fraction bar, there cannot be, I'm going to cross this off, there cannot be a denominator of it. So if you're working on your quiz, test, assignment, and you put a radical in the denominator of a fraction, that's not something that is written in standard form. All right, next part. Product property of square roots. So the product means you're multiplying 2 square roots. Well, what's the property with that? So we have it in detailed in 3 different ways: words, numbers, and algebraic expression. So in words, the square root of a product equals the product of the square roots of the factors. Okay, so that's a lot to see, but let's see a numerical example. So what it's saying, the product of a square root, so we have 9 times 5. That's equal to the product of the square roots of the factors. So this means we could separate this. Instead of representing square root of 9 times 5, we could represent this as square root of 9 times square root of 5. So that's a property that you can use when you're multiplying radicals. And with this, we already know what this thing is equal to. Let's put this in orange. What this is equal to. Right, square root of 9, we know that that is 3. And square root of 5, that cannot be simplified any further, so this is, right, our final answer would be 3 radical 5, or 3 square root of 5. So extending this to kind of some background understanding, if you remember, when we simplify radicals or square roots, right, if you remember way back when, earlier in second semester, we used a factor tree. So factors of 45, we could put 9 and 5, right? That's already what we have here. And you continue the branches of these trees that have still composite factors. So 9 can be broken up with 3 and 3. And we cannot continue. All these numbers are now prime, which means that its only factor are 1 in itself. So we're going to circle pairs. We'll underline singleton numbers. And typically you put the pairs on the outside of the radical and the singleton numbers as the radicand. Okay, so anyways, connecting this to factor trees to now what we've been working on, which is, or we're now working on, is separating into factors. Okay, and then algebra is just saying when you have square root of a times b, this is square root of a times square root of b, and the square root of a and b cannot be, it's saying greater than or equal to 0. They cannot be 0 and they cannot be negative. It's got to be a positive number. Right, specifically for square roots. All right, so we have some examples here. So we're now going to simplify. So product examples. So we could simplify this using factor trees, but since it says a product, I'm going to try to represent this as a product. So square root of 108. I mean, we could put, let's actually put, we're not going to put a complete list, but let's put the list of squares from 1 through 6. So 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and 6 squared. This is equal to 1, 4, 9, 16, 25, 36. So 108, we can actually represent that by a product of one of these numbers. Probably not 1 because 1 doesn't help us, but 4, I think 4 could go into that. 9, maybe 9 could. But we can actually represent this as, and this is something that you would just know if you're off the top of your head. We could use 36. And this could be represented as 36 times 3. Right, 36 times 3 is 108. Right, this means it's because this, right, contains a perfect square. I'm just going to circle this one. All right. Now we said that when we have a product, a square root of a product, we can put that as a product of square roots. So we're going to put this as square root of 36 times square root of 3. They each get their own like house here. And we can simplify the first one, right? Square root of 36, we know that that's 6. And square root of 3, that doesn't simplify. We just write that next to it. So our final answer here is 6 radical 3. All right. Now I'll move on to the next one, which is right, where we now have a number and also a variable. I want you just to understand here that your index is 2. So when we're thinking about it, is we're thinking about, right, what number times itself equals it. So 2 times. So if I put, I'm gonna write that 2 in here. So square root of 9 times x cubed. So to simplify this, right, we're gonna write this as a series of products. I'm going to put 9 times, and what I want you to think about here, and this is something new for variables, is think about like long division. When you think of long division, you think about, right, how many times can a number go into another number without going over? It might have a remainder. So I think about this as how many times can 2 go into 3? Right, I can go into once. So I'm going to write one term here, right? And 2 times 1 is 2, right? And if 2 goes into 3 once, there is a remainder of 1. So I'm going to put another product as x. You can think of this as to the first power. And we know that x squared times x to the first power, that does equal x to the third power. Okay, but what we're going to do is we're going to give each one of the factors in this product its own square root. So we're going to have square root of 9 times square root of x squared times square root of x. I'm actually not going to put that 1 there for the exponent. We'll just keep like this. And then this will actually give us our final answer because the square root of 9 is 3. Square root of x squared, right? What happens here is that the square and the square root cancel out, or since there's an index of 2, you can think of this as 2 divided by 2, which is 1, which means it gets to leave the radical. And it's just x to the first power. And then this final thing, square root of x, since this is second, this is first, right? 2 cannot go into 1. So if you cannot simplify any further, you just write what you see. So what we see is square root of x. So that is our final answer, So 3x times square root of x. Okay, this we're gonna have you'll have quite a few problems like this in your practice. Maybe we'll include some problems as a you-do later on. Okay. All right. So from here, let's go on to the next part, which is, so that was product. Now we're working on quotient, which means to divide. So it says the square root of a quotient equals the quotients of the square roots of the numerator and denominator. So that's a lot to see right here. So let's look at a numerical example. So if we have the square root of 3 over 4, that's equal to, if you just take the square root of each individual thing, this is square root of 3 over the square root of 4. And we can simplify a couple of things there, right? We cannot simplify square root of 3, that stays, right? Square root of 3 is here, I just keep it. But square root of 4 does simplify. Square root of 4 is just equal to 2. And if we look at our conditions here, number 2, no radicands contain fractions, right? We did have a fraction, but notice our final answer, we don't have, a fraction inside of a radical. We just have a radical of the numerator. And third thing, no radicals appear in the denominator of a fraction. Yep, we don't have that. It's simplified to be 2. Okay. And then we'll fill in the blank here. Square root of this could be the square root of a over b, which would be the square root of a divided by the square root of b. And hopefully, right, that square root of b would simplify to be some type of whole number. And this is where a is greater than or equal to 0 and b is also greater than or equal to 0. Again, this just means that they're both positive. They have to be positive. If they are both positive, we can use this property. All right. So looking at our first example, right, we have the square root of 15 over square root of 64. We're going to take the square root of 15 divided by the square root of 64. We're not doing any math, we're just separating. Now square root of 15, right, if we look at these numbers or these factors here, right, 1 doesn't really help us actually, but 4, 9, and 16 is actually going over it. So none of those can actually simplify square root of 15. So square root of 15 will actually just stay the same. And then also separately from that, if you're not sure how to tell, or we can use a factor tree. Its only factors are 3 and 5. We do not see any pairs. They're both singleton numbers. So this is actually as simplified as you can write it. It's just that thing. But on the denominator, square root of 64, that is a perfect square. That is 8. Because 8 times 8 is 64. So no perfect squares within any square root. Right, we don't have a fraction inside of a square root, and our denominator is not a radical. It satisfies all 3 conditions. That means that this is our final answer. Okay. And let's go to the next one. So we're going to separate this into the square root of each part, numerator and denominator. On the numerator, square root of 81 is a perfect square. It's 9. 9 times 9 is 81. And again, when you think about this, our index is 2. Really what you're doing is you're doing 2 divided by 2. We'll probably write this as a rational exponent on the backside, but 2 divided by 2 is just x to the first power, or just x. And again, what really happens here, right, the squares and square roots just cancel out. But we can actually write over here that we divide by 2. This is only for exponents. This does not mean like I don't want you to take this 64 and start dividing it by 2. No. Only for exponents that are within square roots. Okay, so our final answer here is 9 divided by x. Final answer, no square roots at all. So it satisfies all 3 conditions. All right, you know what? Let me give you an example here. I'll give you 2 u-dos. Let's write u-dos off to the left. Okay, I'm gonna give you one product and one fraction. So let's say the first u-do for a product, let's say it's the square root of 16 x to the 7th power. And the fraction, we're going to have the square root of, let's do 25 divided by y to the 8th power. Okay, so I'd like for you to pause the video at this point, try these two problems and see if you can simplify, and when you're done, resume the video. We're going to go over it now, so this is your warning. Just counting down from 3, 2, and 1. Okay, so since this is a product, we're going to separate this into the square root of 16 times the square root of, we could put the square root of 7. But like I said, our index is 2. How many times can 2 go into 7? It can go into 3 times. So we're going to represent this product as, 2 times 3 is 6, so this will be x to the 6th power times x to the, or square root of x. Right, both of these things, I'll put a 1 there, equal x to the 7th power. So again, that question you're asking, well, how many times can 2 go into 7? It's 3. You don't have to write a 3 anywhere, but you're writing 2 times 3, which is 6, and that remainder as well. Okay, square root of 16 is 4. This second one, our index is 2, so you're dividing 6 by 2. That's where that 3 comes from. This is x to the 3rd power. And then this final thing here, it cannot simplify. This is just x to the 1st power, or just square root of x. So this is our final answer. 4x cubed times radical x. Next one. Since we have a fraction, we're going to have to rewrite a square root for each part of the fraction. Square root of 25 is 5. And the denominator, again, we're dividing only for exponents. 8 divided by 2. I didn't have to rewrite this because this is even, so I didn't have to write it as like a remainder. 8 divided by 2 is just 4, so this is y to the 4th power. And that is our final answer. Okay, let's move this over to the back side. We'll get to another example here. So, but this is for cube roots, so we got to be careful. So we do have an index here. The index is 3. So we do want to separate this, though, into the different parts. So we're going to put a cube root of, we'll put a long radical. We can represent this product as our coefficient, 125 times. Now, again, for this part, we're thinking, how many times can 3 go into 7? 3 can go into 7 twice, and 3 times 2 is 6. So this is very similar to like the last one, it's just we have a cube root this time. Now we're going to separate each individual one. So cube root of 125 times cube root of x to the 6th power times cube root of x to the 1st power, but like I said, we're just going to keep that as x. Okay. Now to simplify each part, the cube root of 125, if you have your list of cubes, or you're thinking about what number times itself 3 times equals 125. So right, 2 times 2 times 2, does that equal this? 3 times 3 times 3, does that equal this? You can also do a factor tree for this, right? And in this case, you'd be looking for what, 3 numbers? I mean, we could do it here, actually. This is 25 times 5, and 25 can be broken up in 5 and 5. That is a trio of numbers. It turns out that the cube root of 125 is 5. So this whole entire thing is 5 because 5 times 5 times 5 is the radicand. Next part. Again, what you're doing here is you're just dividing. So this will be x to the 2nd power. But you know what? I do want to show a little bit more of an explanation on this one. Let's put this over here. I'm just going to show some more work. So why is this x to the 6th power? Because when you write this as a rational exponent, we talked about how this is x to the 6, and our index of 3 is actually, it's a fraction, 1/3. I'm going to put this in black. And when you have an exponent to an exponent, that is the power rule, which states that you can multiply those exponents. This is x to the 6 times 1/3. Really what you're doing is just 6 times 1. So this is 6/3, or 6 over 3. And that's why it becomes 2, because 6 divided by 3 is 2. Okay. And then finally, the last part, that's our remainder. Nothing's going to happen with that. We're going to put the cube root of x. Not to confuse the 2 and the 3 being together. That's not a 23. I'll put a dot here so we can separate them. But our final answer is 5x squared times the cube root of x. Okay. And then the last part that we have here is what we call is rationalizing the denominator. Now this is all dealing with item number 3. No radicals appear in the denominator of a fraction. Now, if you ask me, I'm not the biggest proponent of rationalizing the denominator. The purpose of rationalizing the denominator is so that there's some standard answer. And generally textbooks or testing companies, they prefer there to be a standard answer. So for me, just so you know, like I'm okay without it, but our Big Ideas prefers that you rationalize the denominator. So we'll go through a couple examples so you can see it's simple in what you need to do, but it's more complex in the procedure. Okay, there was a mistake here. I did decide to write a couple of cubes. So 1 cubed is 1, 2 cubed, I made a mistake. I put 9, going to put 8. And 3 cubed, 3 times 3 times 3 is 27. We'll get to that later. So what does it mean to rationalize the denominator? Now, a rational number means fraction. So it deals with some type of fraction. When a radical is in the denominator of a fraction, you must multiply that fraction by an appropriate form of 1 to eliminate the radical from the denominator. So what we mean by appropriate form of 1, right? When we multiply fractions to get common denominators, right? This is like 2 divided by 2, 3 divided by 3. It could also even be square root of 2 divided by square root of 2. All of these things, when you have the same thing on the numerator and denominator, they all just equal 1. Okay. So let me go ahead and just put this in the simplest terms I can. This means to multiply the top and bottom by the denominator. But I'm just going to put the bottom number. That's the simplest way I can say it. Whatever the denominator is, you're going to multiply the top and bottom of that. By that, sorry. So our first thing, your first question you should ask yourself, what's the denominator? If it's a radical, this means, and it cannot be simplified, I'm going to multiply the top and bottom by something. Right? If I multiply it by 3, don't write this. Right? 3 divided by 3 is 1. We're going to do something similar to that. We're going to multiply it by that denominator, square root of 3n times square root of 3n. Okay. Now, this actually makes it a little bit easier for the denominator, but I should put a fraction bar. Right, this equals 1. What I wrote here equals 1. But when we multiply, it's going to equal something else for us to write this final answer. I wouldn't say that this is more simplified. It's just a standard way of writing it. So the numerator. We talked about how the product of radicals, you can write that as a product under 1 radical. So let me draw the fraction bar. Square root of 5 times square root of 3n is you just multiply 5 times 3. That's 15n. It's just that it's under 1 radical. On the denominator, put this in a different color. These will always be the same number, and something special happens with that. And this is the whole purpose of rationalizing. Square root of, 3 times 3 at least, is 9. And n times n squared. Okay. It turns out when you rationalize the denominator, you can always get rid of the radical that's on the bottom of that. I'm still going to copy the numerator here, square root of 15n. Nothing's happening with that. But for this part, we can separate this as square root of 9 times square root of n squared. Square root of 9 is 3. Square root of n squared, right? You could think about that as canceling. This is just 3n. this is your final answer. But when you do this, the simplest, another simplest way that I can explain it is that the denominator, once you simplify, will be the radicand. That's the thing that's inside the square root or whatever radical you have. Notice how we have a 3n here? Well, the thing is, that was the radicand of the original denominator. So that's the whole purpose of it. That's what the denominator is of this. So our final answer, this entire thing should actually have a square root, is square root of 15n divided by 3n. You cannot simplify this any further. You cannot simplify anything that's out inside of a radical with something outside of the radical. So don't think that you can divide the 15 by 3, the n divided by the n. Unfortunately, you can't do that. Okay. All right, but let's go through another example, and then we'll have some u-dos. So I see we do not have a radical in the numerator, but we do have a radical in the denominator, which we cannot have. Okay. So the process, whatever that bottom is, multiply the top and bottom by this. And we have a cube root. This is of 9. Okay. Okay. So for this, right, I know this is a crazy looking thing over here. But we're going to have 2 cube root of 9 on the numerator. You cannot simplify, since we have something on the outside and inside, you cannot combine those things. It won't be under one radical. For the denominator, though, we have square root of 9, or sorry, cube root of 9 times cube root of 9. That's going to actually work a little bit differently, though. So we're going to have cube root of 9 times 9 is 81. Okay. It's at this point that we try to see what we can simplify. The cube roots, the reason I wrote this here is that we're going to use this one here. It turns out that there's some product with 27. I believe this is 27 times 3. 60, yeah. So we can represent the denominator here. I'm still going to keep the numerator. We can represent cube root of 81 as cube root of 27 times the cube root of 3, right? 27 times 3 is 81. So that's us using our resources, using maybe a list. But the cube root of 27 is 3 here. So I'm going to rewrite this as 2 cube root of 9 divided by this entire thing is 3. I know there's a lot of 3's going on here. Divided by the cube root of 3. Okay. So at this point, the 2 and the 3 cannot be simplified. The cube root of 9 and cube root of 3 also can't be simplified. So in this case, it does turn out where you have to actually multiply another root. Since I still have a root in the denominator, we cannot have that. I'm going to have to multiply again. In this case, it's a different one. It's a cube root of 3. Okay. So in this step, I can actually, this is a complex problem, but I can now multiply this. I can now multiply this. We're going to have 2 cube root of, on the numerator, 9 times 3 is 27. Oh, sorry. 9 times 3, 27. Oh, yeah, okay. And the denominator, we're still going to have this 3 that I didn't highlight, but the things I did highlight in red, the cube root of 3 times the cube root of 3 is 9. How can we simplify this? Oh, okay. I did make a mistake here. You have to multiply by the entire denominator. So the entire denominator is 3 cube root of 3. So that was my mistake. So when I do multiplies, 3 times 3, we're going to have 9 right here. And then right here, this 2 times 3, let's erase that. This should be a 6. I think that should work out. Okay. Now at this step, I think I made a mistake here. You know what? I'm gonna cross this off. Let me do one thing here. This is actually how we should have done this problem. Looking back at it, actually, we should have actually multiplied by the cube root of 3. So that's my fault. The reason is because what we want to do is we want to get one of these numbers, and this can become a 27. So here we're going to have 2 cube root of 3, and this right here, 9 times 3 is 27. So cube root of 27. And actually this is our final answer. The next step is our final answer, because we're going to have 2 cube root of 3, and the cube root of 27 is 3. And this is how we get rid of the denominator on, the radical on the denominator. So really what we're thinking about, since this wasn't a square, that rule doesn't apply exactly. We just have to think about what number can we get in this list of cubes. We're trying to get that 27 because that does simplify to be a rational number or a whole number. So this, I apologize for this. This stuff you can just cross off, but I'll just delete this for now. Okay, but let me give you a you-do. This is going to be a lot simpler than the one that we just did. This is probably like a harder one off to the right, but you-do. We're going to have square root of 5 divided by square root of 2. I'd like for you to try to simplify that. I'll let you work it out, but you're welcome to continue the video. For right now, I'm going to go and go over it, but give it a shot. You would multiply by the square root of the denominator, which is square root of 2. Okay. The square root of 5 times square root of 2 is square root of 10. Square root of 2 divided by square root of 2, or times square root of 2, is square root of 4. But we know that when we multiply the same thing, it should be that radicand. So this actually simplifies to be square root of 10 divided by square root of 4 is 2. And this is actually our final answer. Square root of 10 cannot be simplified any further. There's no perfect squares at all. These are both singleton numbers, so if we were to simplify this, it's already in most simplified form. So our final answer is square root of 10 over 2. All right. Let me know if you have any questions. Apologize for this problem, but the strategy for this is try to get the denominator to be one of these cubes. That's only for cube roots. For square roots, a lot easier. Just multiply by the denominator. Okay. All right.